So, we're constantly faced with trying to figure things out.
Absolutely.
Whether it's, looking at data at work, trying to see what's really going on, or even just understanding different viewpoints, it always kind of boils down to choosing between different explanations.
Hmm.
That feels like a pretty fundamental challenge for anyone who's trying to learn something new. The learner, you could say.
Definitely. And that's exactly where this thing called the minimum description length principle, or MDL,
Mm-hmm.
offers a really powerful way forward.
MDL.
Yeah. And the core idea, which might sound a bit surprising at first, is that learning, learning is actually all about data compression.
Data compression. As learning. Okay, hold on. Let's unpack that.
Yeah.
Because when we learn something, we usually feel like we're gaining information, right?
Yeah.
Not making it smaller. How does that work?
Right. Feels counterintuitive.
Hmm.
But it's really about finding the hidden patterns, the regularity. Think
Yeah.
about it. If you can describe a whole bunch of information in a shorter way than just listing every single piece, you've essentially identified some underlying structure. You've found something. And that structure, that regularity you've spotted, that's the essence of what you've learned.
Ah, I see. The description gets shorter because you found the rule.
Exactly. So this deep dive is really all about understanding how MDL uses this core idea.
Okay, so our goal today, our mission, is to really get to grips with the main ideas behind MDL.
Hmm.
We want to see how it helps us choose between different explanations, different models maybe, and why it's actually relevant for, anyone dealing with data and trying to build a clearer picture.
Yeah, and the sources we're drawing on are specifically focused on introducing and explaining the principle.
Yeah.
So they should give us a good foundation.
Great. So let's dive into that core concept then. Learning as compression. You mentioned coin flips.
Yeah, let's use an example. Imagine you've got three big sets of coin flip results, say 10,000 flips each.
Okay,
The first set looks really simple. Heads, tails just repeated over and over again.
got it. Very predictable.
The second set looks completely random, like just pure chance, no obvious order at all.
Okay, like static.
And the third set, it has a lot more heads than tails, but it's not a perfect pattern. Maybe like 75% heads.
Right, so one's super pattern, one's totally random, and one has a sort of statistical lean. My brain immediately starts sorting those.
Exactly. Your intuition tells you the first sequence, the heads, tails one, has a clear pattern. And because it has that pattern, we can describe it really simply.
Yeah, you wouldn't list them all out.
No way. You just say, repeat heads, tails 5,000 times. That description is way, way shorter than writing down 10,000 individual flips.
Okay, that's compression. Obvious compression. The pattern is the compression.
That's the key insight. Finding the pattern lets you compress the data. The pattern is the learned information in this MDL view.
Okay, I'm with you. So what about the second set, the one that looked totally random?
This is where it gets really interesting, philosophically almost. It turns out that for a sequence that's truly mathematically random, the shortest way to describe it is usually just to write out the sequence itself.
Really? There's no shortcut?
Basically, no. There's no simpler program or description you can write because there's no underlying pattern to exploit. It's essentially incompressible.
Wow. So in MDL terms, if you can't compress it, you haven't really learned anything concise about it. Is that fair?
That's a good way to put it. No pattern means no compression, which means no real learning in this specific sense.
Okay. And the third sequence, the one with more heads. It wasn't perfectly patterned, but it wasn't random either.
Precisely. And you can still compress that one, just maybe not as dramatically as the first one.
How so?
Well, you could describe it by saying something like, generate a sequence of 10,000 flips where the probability of heads is about 0.75.
Ah, right. You state the bias.
Yeah. That description, plus maybe some info about the specific deviations, is still likely shorter than listing all 10,000 results. You've identified a statistical regularity that bias towards heads, and that allows for some compression. You've learned something about the underlying process.
Okay, I'm definitely starting to see the connection now. The more regularity, the more compression, and that's how MDL frames learning. You mentioned this isn't just for coin flips, right? It applies more broadly.
Well, absolutely. Massively broader. Think about the digits of pi.
Okay. Infinite non-repeating sequence.
Right. Seems randomish locally.
Right.
But we have relatively short mathematical formulas, algorithms that can generate as many digits as we want. That formula is an incredibly compressed representation of that infinite sequence.
That's a great example. The formula is the short description.
Or think about physics. Newton's laws of motion. Those laws are very concise descriptions, right?
Yeah, F and all that.
But they allow us to predict and therefore implicitly compress a huge amount of data about how objects move, baseballs, planets, whatever. Instead of listing every position at every moment, you just give the law and the initial conditions.
Compression again. And language.
Same idea. Grammar is a form of compression. It provides rules, structure. Because we have grammar, we don't need to spell out every single relationship between words from scratch every time we speak or write. The rules let us be more efficient.
So this idea of the shortest description seems really fundamental across different domains. Is there like a formal way to define what that means? The shortest possible description?
Yes, absolutely.
Yeah.
That leads us to a concept called Kolmogorov complexity. It's a bit theoretical, but really important background.
Okay. Kolmogorov complexity.
Basically, it's defined as the length of the shortest possible computer program, written in some fixed universal programming language that can produce a specific piece of data, like our sequence of coin flips, and then halt.
Shortest program. Okay. So a shorter program implies lower complexity, more regularity in the data.
Exactly. If the data has a pattern, you can write a short program to generate it. If it's random, the shortest program is basically just print this long string of data.
Now, does it matter which programming language you use, like Python versus C++ or something?
That's a good question. You might worry it does. But there's something called the invariance theorem. It essentially says that for reasonably long sequences of data, the choice of programming language doesn't fundamentally change the complexity.
Oh, so?
Well, the length of the shortest program might differ, but only by a constant amount that depends just on the languages, not on the data itself. For long data strings, that constant difference becomes negligible. So it's considered a pretty universal, objective measure of the inherent complexity or regularity of the data.
That's useful. So it's not just about finding some clever coding trick in one specific language.
Right, and this concept is so powerful. One of the pioneers, Ray Saramonov, even suggested that the best explanation for any set of observations is simply the shortest program that could have generated it.
Wow. That's a bold statement. The
Yeah.
shortest program is the best explanation.
Yeah, that's the core idea behind what's called ideal MDL. It uses this Kolmogorov complexity directly.
Ideal MDL. Okay, sounds great, but I sense a but coming.
You sense correctly. There's a huge practical problem.
Oh.
Kolmogorov complexity is uncomputable,
Uncomputable, meaning?
meaning there's no general algorithm that can take any piece of data and actually find or calculate the length of the absolute shortest program that generates it. It's related to the halting problem in computer science, if you've heard of that.
Ah, okay, so it's a fantastic theoretical concept, like a perfect measure of complexity, but not something we can actually point a computer at and say, find this.
Precisely. So we can't directly implement ideal MDL most of the time.
Okay, so how do we bridge that gap? How do we go from this beautiful but unusable ideal MDL to something we can actually work with?
That's where practical MDL comes into play.
Practical MDL.
Right. Instead of searching through the infinite space of all possible computer programs, we restrict ourselves. We choose a specific, limited set of description methods or models that we think are relevant.
Like deciding we'll only consider explanations that are, say, polynomial equations, or maybe specific types of statistical distributions.
Exactly. We might decide to only look at linear models, or polynomials up to a certain degree, or Gaussian distributions, whatever seems appropriate for the problem.
Yeah.
By restricting the types of descriptions, the types of programs we allow.
We lose the guarantee of finding the absolute shortest description overall.
Correct. We might miss some really clever short description that uses a method outside our chosen set.
Yeah.
But, crucially, we gain the ability to actually find and calculate the shortest description within that restricted set. It becomes a computable, practical problem.
So it's a trade-off. We give up on absolute optimality, perhaps, but we gain something usable. And presumably, our knowledge of the problem helps us choose a sensible set of models to consider.
Yes, absolutely. Prior knowledge, scientific understanding, domain expertise, they all guide us in selecting a useful class of models or description methods to work with in practical MDL.
Okay, that makes sense. So within this practical framework, how does MDL help us actually choose between different models or explanations? This is the model selection part, right?
Exactly. This is where MDL really shines in practice model selection. We often have several competing hypotheses or models for our data.
Right, like fitting a curve to some data points. Should it be a straight line? A parabola? Something more complicated?
A perfect example. A simple straight line might be too basic, it underfits, misses the real trend.
Yeah, doesn't capture the curve.
A very complex, wiggly polynomial might go through every single data point perfectly.
Looks great on this data.
But it's probably just fitting the noise.
Yeah.
It'll likely be terrible at predicting any new data points. That's overfitting.
Right, the classic problem. We need to find that sweet spot, a model that captures the genuine pattern without getting bogged down in the random fluctuations, the noise.
Precisely. We want a model that generalizes well. So how does MDL help us find that balance?
Yeah, what's the MDL approach?
The first, sort of simplest version, often called crude or two-part MDL, gives us a basic recipe. So
Wow.
it says, choose the hypothesis, the model, that minimizes the total description length.
Total description length.
It's broken into two parts. First, the length needed to describe the hypothesis or model itself. Let's call that L hypothesis.
Okay, how complex is the explanation?
And second, the length needed to describe the data given that hypothesis, L data hypothesis.
So how well does the explanation fit the data? Or maybe how much extra information do you need to specify the data once you have the explanation?
Exactly that. You add those two lengths together, L hypothesis plus L data hypothesis. The model that makes this sum the smallest is the one MDL prefers.
Okay, that has a really nice intuitive feel to it.
Yeah.
A very simple model will have a short L hypothesis, right?
Yep.
But if it's too simple, it won't fit the data well, so the description of the data given the hypothesis, basically, the errors or deviations will be long. L data hypothesis will be big.
Correct.
On the other hand, a very complex model might have a long L hypothesis,
Takes more bits to describe the wiggly line itself.
but if it fits the data perfectly, maybe L data hypothesis is very short because there are no errors to describe.
Right. So MDL automatically balances these two. It's looking for the model that provides the best trade-off, the best overall compression of the data when you account for both describing the model and describing the data using the model.
So in our curve fitting example, L hypothesis is like the complexity of the equation, linear, quadratic, etc. And L data hypothesis is how much information we need to encode the differences, the residuals between the curve and the actual data points.
That's a great way to think about it.
Yeah.
The better the curve fits, the smaller the residuals, and generally the shorter the code needed to describe them.
Okay, this crude two-part MDL sounds pretty compelling, simple and intuitive, but you called it crude, so I'm guessing it's not the full story. What are the issues?
The main issue, and it's a significant one, is that the first part, L hypothesis, how we actually encode the description of the model itself, can be quite, well, arbitrary.
Arbitrary. How so?
Well, you have to choose some coding scheme to turn your model description into a length, into bits. And different choices for that coding scheme can actually lead you to prefer different models, even when looking at the exact same data.
Ah. So the choice of how I write down the description of a straight line versus a parabola could influence which one looks better according to this rule. That doesn't sound ideal.
It's not.
Yeah.
It introduces a level of subjectivity we want to avoid. We need a more objective, more principled way to measure the complexity of a model class that doesn't depend so much on a specific, potentially biased encoding scheme we just happen to pick.
Right. The measure of complexity shouldn't just be an artifact of how we decided to code things up today. It should reflect something more fundamental about the model itself.
Exactly. We need to refine this.
So how do we refine it? How do we get around this arbitrariness in describing the model?
The key idea is to move towards using what are called universal codes and universal models.
Universal codes. Okay, sounds important.
A universal code, in this context, is like a super efficient compression algorithm. It's designed to compress data well across a whole class of possible sources or patterns, even if you don't know in advance which specific pattern the data actually follows.
So it's generally good, not just optimized for one specific type of data.
Right. Ideally, it performs almost as well, meaning it produces a description almost as short as the best possible code you could have designed if you had known the true underlying pattern in hindsight.
Wow. How does that work?
A simple type of universal code is actually related to our crude MDL, a two-part code. First, you use some bits to specify which code or model from a predefined family you're going to use. Then you use that chosen code to encode the data.
Okay, so describing the tool adds a bit to the total length, acting like a penalty for picking a more complex tool.
Precisely. That overhead cost for describing the model becomes part of the total code length. Now, from these universal codes, we can derive corresponding probability distributions called universal models.
Ah, connecting coding back to probability distributions.
Yes. These universal models assign probabilities, which correspond to code lengths, to data sequences, in a way that reflects this idea of good performance across a range of possibilities. One important type you might hear about is the Bayesian universal model.
Bayesian. So this is where Bayesian statistics connects with MDL.
It's one major connection, yes.
Like
The Bayesian universal model essentially averages over all the models within a class, weighted by some prior beliefs about which model is more likely. It gives you a single predictive distribution.
Okay. But MDL isn't just Bayesian, right? Are there other key universal models?
Absolutely. And perhaps even more central to modern MDL is the normalized maximum likelihood, or NML, distribution.
NML, normalized maximum likelihood. Okay, what's the idea there?
NML takes a slightly different philosophical approach. Instead of averaging based on priors, it tries to find a single distribution within the model class that minimizes the maximum regret.
Regret meaning?
Regret here means the extra code length, the extra bits you needed to encode your data using this NML distribution, compared to how well you could have done if you'd known the absolute best-fitting parameters for your specific data in hindsight.
Ah, so it's trying to be as close as possible to the perfect hindsight predictor uniformly across all possible data sets.
Kind of, yeah. It aims for optimal performance in a worst-case sense over the data, minimizing that maximum difference. It's a very clever construction. And the code length associated with this NML distribution for a given data set is called the stochastic complexity.
Stochastic complexity. So that's the key measure in refined MDL.
That's right. The complexity of the model class for a given amount of data is intrinsically linked to this NML distribution and its normalizing factor.
Okay, so refined MDL isn't about L hypothesis plus L data hypothesis anymore, not explicitly.
Not in that simple two-part way. Instead, refined MDL says, choose the model class,
Right.
e.g. linear models, quadratic models, that results in the smallest stochastic complexity for your observed data.
And this stochastic complexity, derived from NML, somehow automatically balances the model's complexity and its goodness of fit to the data.
Exactly. It inherently captures both aspects. A model class that is too simple won't allow a good fit, leading to high stochastic complexity. A model class that is too complex might fit the current data well, but the price for that flexibility related to the NML normalization also increases the stochastic complexity. MDL finds the model class that hits the sweet spot, minimizing this single quantity.
That sounds much more principled than the crude version, less arbitrary. Now, you mentioned before that there are different ways to interpret what MDL is actually doing, what it means when it picks a model.
Yes, there are several really insightful ways to look at refined MDL. Four main interpretations stand out.
Okay, let's hear them.
The first interpretation takes us right back to where we started, compression.
Makes sense.
Refined MDL, using the NML code, or related universal codes, essentially picks the model class that allows for the most compression of the observed data. A better fit leads to shorter code lengths via the likelihood part. But the NML normalization term penalizes models that are too flexible. Crucially, within a chosen model class, NML doesn't inherently prefer any specific parameter value beforehand. It lets the data determine the best fit.
So, still fundamentally about finding the best way to shrink the data description, but using a more sophisticated integrated measure. Got it. What's the second view?
The second interpretation is about counting. It's a bit more abstract.
Counting what?
Roughly speaking, the complexity part of the stochastic complexity, the part that penalizes complex models, can be thought of as related to the logarithm of the number of distinguishable distributions within that model class.
Distinguishable distributions.
Yeah, think of it like this. How many fundamentally different patterns or data-generating processes can this model class actually represent? A more flexible model class, like higher-degree polynomials, can represent many more distinct patterns.
Ah, so it has more options for explaining the data.
Exactly. And MDL penalizes models with too many options because that increases the risk of just happening to match the noise in our specific data set, overfitting. This counting view quantifies that effective number of distinct possibilities the model offers. For certain standard models and large data sets, this complexity term even approximates the log of the number of parameters.
Interesting. So complexity isn't just having more parameters, it's about having more distinct explanatory power, which MDL carefully accounts for. Okay, what was the third interpretation? You mentioned Bayesian earlier.
Yes, the third is the Bayesian connection. As we touched on, refined MDL turns out to be very closely related to Bayesian model selection, especially under certain conditions.
With conditions.
Particularly when Bayesian methods use what are called non-informative or objective priors, like the Jeffreys prior. These priors are designed to let the data influence the conclusion as much as possible, rather than relying heavily on pre-existing beliefs. In many common situations, especially with larger amounts of data, choosing the model with a minimum stochastic complexity, MDL, leads to the exact same model choice as picking the model with the highest posterior probability using these specific Bayesian priors.
So different philosophies minimizing description length versus updating beliefs, but they often converge on the same answer in practice.
Often, yes, for large sample sizes. It suggests a deep connection, though the interpretations remain distinct. MDL doesn't require the concept of prior beliefs in the same way Bayesian methods do.
Fascinating. And the fourth interpretation.
The fourth is the prequential or predictive interpretation. This one's really appealing, I think.
Frequential, like predicting sequentially.
Exactly. Think of any probability distribution or any coding scheme as a strategy for making predictions. Given the data you've seen so far, what do you predict will come next?
Okay, yeah, a model should help you predict.
The prequential view says that MDL effectively selects the model that would have performed best as a sequential prediction strategy. You feed the data points in one by one. After each point, the model updates and predicts the next point. You measure the accumulated prediction error, or equivalently, the accumulated code length needed for the actual outcomes based on the predictions.
Ah, so you're evaluating how well the model learned and generalized as the data was coming in.
Precisely. MDL favors the model that minimizes this total accumulated prediction error or code length. It's seen as a very honest evaluation because the prediction for each data point is made before seeing that data point, using only the past data. It directly tests the model's ability to generalize.
That makes a lot of sense. It prevents you from just finding a complex model that fits everything perfectly only after you've seen all the data. You have to commit to predictions along the way.
Right. It rewards models that learn the underlying structure quickly and use it to make good forecasts.
4 interpretations: compression, counting, Bayesian connection, and prediction. That gives a really rich picture of what MDL is doing. Now, you mentioned challenges. What happens when things get more complicated? Like, what if we have infinitely many models to choose from? Or what if this NML thing, the stochastic complexity, runs into problems?
Those are definitely key points when we push MDL further. Dealing with infinitely many models is a common scenario. Think about polynomial fitting. You could potentially consider polynomials of any degree.
Right, degree 1, 2, 3, up to infinity. You can't just calculate stochastic complexity for all of them.
Exactly. The basic MDL approach compares a finite set of models. To handle infinite sets, we usually need to add another layer. One common way is to assign a cost, or prior probability, which translates to a code length, to considering each model or each family of models.
How would it work?
For instance, if our models can be indexed by integers, like polynomial degree 1, 2, 3, we could use a universal code for integers to describe the index d. The length of this code, LD, would then be added to the stochastic complexity of the model with that index, say SE data mild, would minimize LD plus SE data model.
So simpler models, lower index D, get a shorter LD prefix code, giving them an advantage. It penalizes considering increasingly complex model families.
Yes, it introduces a penalty for even entertaining more complex types of models from the infinite hierarchy.
Okay, that seems like a reasonable way to manage infinite choices. What about the other issue? When does the stochastic complexity itself become problematic? You said NML might not always work.
Right. There are situations, even with seemingly simple model classes, where the NML distribution isn't well defined because its normalizing factor becomes infinite. This is sometimes called the infinity problem in MDL.
When would that happen?
A classic example is a simple Gaussian model for IID data, where you estimate the mean, but you allow the mean to be any real number without restriction. The integral needed to normalize the likelihood over all possible means diverges.
Ah, because there are too many possibilities in an unbounded space.
Essentially, yes. The model is, in a sense, too flexible relative to the data. To handle this, researchers have developed extensions and modifications. One idea involves meta-universal models. For example, you might restrict the parameters to lie within some range, calculate NML within that range, and then also encode the range itself.
So you encode bounds first.
Or there's an approach called renormalized maximum likelihood, RNML. It's a bit technical, but it essentially modifies the likelihood calculation based on the data itself to ensure things stay finite.
Okay, so there are advanced techniques to make MDL robust even in these trickier, more mathematically involved situations. It sounds like a very adaptable framework overall. You focused a lot on model selection. Does MDL do other things in statistics?
Oh, definitely. It's not just about choosing between predefined models, although that's a major application. MDL principles extend to other areas of inference, too.
Like what?
Well, it can be used for non-parametric inference. That's where you're trying to learn about the structure of the data, maybe estimate a density function, without assuming it belongs to a simple predefined family, like Gaussian or Poisson. MDL helps find a good balance between flexibility and data fit there too.
Okay, learning structure without strong assumptions. What else?
Parameter estimation. Even if you've selected a model, say a Gaussian distribution, MDL offers perspectives on how to estimate its parameters, like the mean and variance. You could choose the parameters that minimize the two-part code length, or use parameters derived from the predictive MDL approach. Often this leads to maximum likelihood estimates, but sometimes MDL suggests subtle adjustments.
So it can guide how you tune the knobs within a chosen model, not just which model to pick. And regression, like finding the relationship between variables.
Yes, in regression, MDL is very useful. Say you're trying to predict Y based on several potential predictor variables, x1, x2, x3. MDL can help decide which subset of x's to include in the model.
Feature selection, basically.
Exactly. And also, what form the relationship should take. Should it be linear? Should we include interaction terms, maybe use polynomial terms for some x's? MDL evaluates these different regression models by considering the code length needed to specify the chosen predictors and their functional form, plus the code length needed to describe the residuals, the prediction errors.
So it helps choose both the variables and the complexity of the relationship, balancing fit and parsimony. It really does seem widely applicable. How does it sit alongside other big ideas in statistics and machine learning, things listeners might have encountered?
Good question. It's helpful to compare and contrast. First, remember, when we say MDL in this context, we generally mean this modern approach based on universal codes and models like NML, focusing on minimizing stochastic complexity or related predictive measures.
Right, the refined version.
Okay, so comparing it to Bayesian inference. As we discussed, there are strong connections, especially with certain priors. Both aim to balance fit and complexity. However, MDL frames everything in terms of code lengths and compression derived from information theory. It doesn't necessarily require subjective prior probabilities in the same way Bayesian methods often do.
And you mentioned MDL might handle cases where models are known to be imperfect differently.
Yes, MDL is sometimes seen as more naturally handling situations where we believe all our candidate models are likely wrong. There's the approximations of reality. MDL seeks the model that provides the best compression, the best summary of the data among the available options, without necessarily assuming one of them is the true data-generating process. Bayesian methods can struggle a bit more conceptually here, though practical approaches exist.
Okay, so similar goals, related results sometimes, but different philosophical underpinnings. What about BIC, the Bayesian Information Criterion? People often mention BIC and MDL together.
Ah, yes, that's a very common point of confusion. BIC looks similar to some older, simpler forms of MDL or approximations to Bayesian evidence. It includes a term for model fit, likelihood, and a penalty term based on the number of parameters and the amount of data, k log n.
Right, I've seen that formula.
But it's crucial to understand that BIC is generally just an asymptotic approximation. It becomes accurate only for very large data sets and under specific assumptions about the models. Refined MDL, based on NML or similar universal codes, is often much more accurate, especially for smaller data sets or when comparing models with very different structures or effective complexities that aren't simply captured by the parameter count.
So BIC is like a rough and ready approximation, while MDL aims for a more precise measure of complexity and fit. They aren't the same thing.
Definitely not interchangeable. Using BIC is not the same as applying the MDL principle in its refined form. Sometimes they agree, often they don't, especially in tricky cases.
Good clarification. What about MML, minimum message length? Sounds similar.
It does sound similar. MML is another information theoretic approach to inference, developed largely independently by Wallace and Bolton in Australia, around the same time Rissanen was developing MDL. It also aims to minimize the length of a message that encodes both the model and the data.
So what's the difference?
The main technical difference lies in how they design the codes and measure the message length. MML often focuses on minimizing the expected message length, integrating over parameter uncertainty using a prior. MDL, particularly NML-based MDL, tends to focus on minimizing worst-case regret or using specific universal codes. They often lead to similar results but differ in their precise formulation and philosophical justifications. Think of them as close cousins with slightly different ways of thinking.
Okay, related but distinct. And frequential analysis, you mentioned that connection earlier.
Yes, the link to frequential analysis, or predictive validation, is very strong and fundamental to one of MDL's key interpretations. As we said, MDL, via universal codes, inherently defines sequential prediction strategies. Evaluating models based on their cumulative prediction error, as done in frequential analysis, aligns perfectly with the MDL goal of finding the model that best compresses the data sequentially. This predictive view also connects MDL conceptually to methods like cross-validation, which also aim to assess a model's predictive or generalization performance.
It really seems like MDL provides this unifying lens connecting compression, complexity, prediction, and inference. It sits at a fascinating intersection. But no framework is perfect. Are there common criticisms or known problems with MDL we should acknowledge?
Yes, definitely. Like any powerful tool, it has limitations and faces critiques.
Such as?
Well, one conceptual criticism sometimes raised is that the whole idea of Occam's razor, that simpler explanations are better, which underlies MDL, is just a philosophical preference, maybe arbitrary. Why should the universe favor simplicity?
Right. Why should shorter descriptions be truer?
MDL advocates would respond that, especially in refined MDL comparing well-defined models, the principle isn't arbitrary. It emerges naturally from the mathematics of coding and prediction. The NML framework, when it applies, provides a non-arbitrary way to balance fit and complexity. The subjectivity really creeps in more when dealing with infinite model classes or ill-defined complexities, but MDL offers principled ways to handle those too, arguably better than just ad hoc penalties.
So the framework itself tries to be rigorous where possible. What about practical problems?
A major practical challenge is actually computing the NML distribution, or the stochastic complexity. For many interesting model classes, it's mathematically difficult or computationally intensive.
So the ideal calculation might be hard.
Exactly, which means in practice, people often have to rely on approximations, like asymptotic formulas, which sometimes resemble BIC, adding to the confusion, or specific methods for certain model types. You have to be careful when using these approximations, especially if the conditions for them aren't fully met.
So calculation can be a hurdle. Any other issues?
Another point to remember is that MDL, like most model selection methods, chooses the best model from the set you give it.
Right. Garbage in, garbage out, potentially.
Kind of. If all the models you're considering are actually terrible representations of the real data generating process, MDL will dutifully pick the least bad one according to its criterion. But that least bad model might still be quite wrong or misleading about the underlying reality. MDL doesn't magically find the truth if the truth isn't among the options considered.
That's a crucial caveat for any modeling effort, really. Know the limitations of your candidate models. So it seems like MDL is a powerful tool, but you need to understand its principles, its calculation challenges, and its scope.
Absolutely. You need to be aware of when it's most effective and when caution is needed. But yes, overall, it provides a really coherent and insightful way to think about learning, inference, and finding structure in data.
Okay, let's try to wrap this up. What's the absolute core takeaway from this deep dive into MDL?
I think it's that fundamental insight. Learning is compression. Finding regularity, finding patterns, allows you to describe things more efficiently. MDL formalizes this intuition into a rigorous statistical principle.
And the key practical implication.
It gives us a principled way to tackle that fundamental problem of model selection. How to balance the complexity of our explanation against how well it fits the data we see. It avoids overfitting by automatically penalizing models that are too flexible.
Plus, it has these surprising and deep connections to information theory, counting arguments, Bayesian ideas, and maybe most intuitively to making good predictions.
Exactly. It offers this a versatile framework for understanding and learning from data. And importantly, it doesn't strictly require us to assume that one of our models is the absolute truth. It's about finding the best description, the best summary among the options available.
So if listeners want to dig deeper after this discussion, where might they look?
Well, depending on their interest, they could look for applications of MDL in their specific field. It's used in bioinformatics, image analysis, time series, machine learning theory, and more.
Find concrete examples.
Yeah. Or, for the more theoretically inclined, diving into the mathematical details of universal coding, stochastic complexity, and the derivation of the NML distribution would be the next step. Peter Grunwald's book on MDL is a comprehensive resource.
Great. This has been genuinely fascinating. It's really shifted my perspective on what it means to find patterns and learn from information.
It has a way of doing that.
And that really brings us to our final thought for you, the listener. Thinking about everything we've discussed, how might this core idea of compression change the way you evaluate different explanations or theories, whether it's in your professional field or just in navigating the complexities of everyday life? Is the simplest explanation the one that allows for the most compression, often the most insightful? It's definitely something to chew on.
A very provocative thought indeed.
Thanks for joining us on the deep dive.